The Sun, the heart of our solar system, is a yellow dwarf star, a hot ball of glowing gases. Its gravity holds the solar system together, keeping everything from the biggest planet to the smallest particles of debris in its orbit. Electrical current in the Sun generates a magnetic field that is carried out through the solar system by the solar wind, a stream of electrically charged gas blowing outward from the Sun in all directions. The connection and interaction between the Sun and the Earth drive the season, ocean current, weather, climate, radiation belt, and auroras. Though it is special to us, there are billions of stars like our Sun scattered across the Milky Way. I want to point out right off the beginning that anytime we talk about the Sun, it's important to note, never look at the Sun without proper eye protection. The Sun is in the center of our solar system. We have the 8 planets and the dwarf planet like Pluto. There are billions of stars like our Sun, but this is our star, the Sun. The Sun is also known as Sol, and we totally rely on the Sun. The Sun is at the center of our solar system. It's responsible for the Earth's climate and weather. The approximate age is about 4.6 billion years old, and is considered to be a yellow dwarf star, a G-type. Has a diameter of about 864,000 miles, has the average distance about 93 million miles away from the Earth. The surface temperature is just under 10,000 degrees. The Sun is the source of energy for ocean currents, drives the water cycle, and drives the weather. And it also creates the wind. So we see in the diagram here how it becomes a very important part of the water cycle here on Earth. And the Sun is also the source of energy, and plants need it for photosynthesis. And it can provide the heat as well. And the average distance between the Earth and the Sun is about roughly 93 million miles. As the Earth goes around the Sun, which is kind of an egg-like orbit, there's a point in time, like in January, that between the Earth and the Sun, it's called its perihelion. Right? And then in July, which is coming up, aphelion on July 2nd. So when we see the Sun, like in the month of June, the Sun is at its highest point for the year, 68 degrees. So we notice that the Sun is providing long days and short nights. That's because the Earth is tilted at 23.5 degrees. Okay? And so what's happening here is because of the Earth tilt, we see that summer is in the northern hemisphere, winter is in the southern hemisphere. And on the solstice coming up in June, we'll see our longest day of the year. And this is all because of the tilt of the Earth. How big is the Sun? Well, it's about 110 times wider than the Earth, or 1.3 million times bigger than the Earth. So you can see right there how small the Earth is in comparison to the Sun. And here's kind of a diagram of the what we call the Sun, and show you some features of it. We have the core, we have the corona, the prominences, large eruptive prominences, the coronal loop. So all these are associated with the Sun, and pretty standard what we say that we see a star. This is kind of the layout of the Sun, or the star. And then, talked about temperature earlier. The temperature inside the Sun can be about 27 million degrees. Okay? And the Sun is generated, the energy is generated by nuclear fusion, as hydrogen is converted to helium and expand. And so what happens when it reaches the surface, even though 27 million degrees at the central core, the surface temperature is about 10,000 degrees Fahrenheit. And now the biggest science mystery is in the atmosphere it goes up to 1,000,000 degrees again. And so that's kind of the search right now to understand what's causing that temperature to go from 10,000 up to 1,000,000 instantaneously. Also important to know with the sun, the radiation that we receive from the sun, it's called electromagnetic spectrum, we see these energy coming towards the sun, from the sun. We have the visible light, which is called white light, okay? But then we have what we call the different filters, or the Earth's atmosphere filter out the frequency. Okay? And so what we see is that we have the short wave, starting with the gamma rays, X-rays, ultraviolet, visible, infrared, and radio. Those are the long waves. Okay? And so when we look at the energy, the Earth is providing, the Earth's atmosphere is providing the filter out a lot of the energy from reaching the ground. And especially in this area here in the short wave, gamma rays here, that we are protected from those, which is a good thing. And then X-rays, UV, and visible. And that's where we start seeing some of it going almost to the ground. But the visible is not what we see. That's why we can see the color, is that the white light from the sun is being spread, absorbed, refracted. That's why we see green and the colors around it. Some are being absorbed, some are being reflected. And then we have the infrared, and radio becomes a long wave. Right? And so you notice too that we have a lot of orbiting Earth observing system where we have certain satellites that specialize in looking at gamma rays and X-rays and UV from outside the Earth's atmosphere. But then after that, we have like TV signal, we have radio telescope here on the ground here on Earth. And that's because radio waves can reach the surface of the Earth. So that's the Earth's magnetic system. Okay. So we're back at the sun. A lot of things that we can associate with the sun is, one is that the sunlight, it creates what we call the blue sky that we see during the day. And what's happening there is that the white light is being refracted into the colors that we recognize, and the blue light is being scattered by the gas molecules and atoms here on Earth. Okay? So we get the direct light, we get the white light, but the blue gets scattered, and that's why we see blue skies during the day. But at night, when the sun is below the horizon, if we don't see that blue anymore. And that's because there's no sunlight being scattered. So that's one thing you can see. Another thing too, that every once in a while you'll see a weather forecast. And in the weather forecast you have a UV index, like this one right here. Okay, so here we are, this early June, still getting a lot of clouds and rain, so it's very low at this time. Right? But if you look during the summer, that's when we notice that in the UV index goes up in June, July, and August here in the Portland area. So that's another association with our sun. And across the United States, you'll see that down in the south, the UV index is particularly high because they have a lot of sunshine, but also up in the Rocky Mountains, in higher altitude. Okay? So the higher altitude that you're up, the more exposure you get to UV. So that's why it's important to pay attention to the weather forecast, and every once in a while you'll get a UV index, and then where you want to protect yourself from the sun, including being in the shade from the sunlight, cover up this exposed skin, perhaps wearing white so it's being reflected, wearing polarized sunglasses to protect the eyes, wear a hat is another good idea, and then also providing the right kind of sunblock to protect your skin. And generally, we look at SPF 15 plus that is recommended from getting you sunburn, or more importantly, protect from you getting skin cancer. A few more facts about the sun. The sun has a very strong magnetic field. Okay? And so that's why we have some solar observatories like Parker and SDO and Soho that are observing the sun and studying it closely so that we have a better understanding of the characteristics of the sun. And so it has a very strong magnetic field, which is really actually pretty important. When we get to it, when we study the sun through special filters like this, at the equator, the sun rotates once every 25.4 days. That's around the equator, right around here. Okay? But at the pole, it's 36 days. So what that means, that around the equator is moving around faster than at the poles. This is called differential rotation. Now, going into that, you look at this graphics here. Because of that, okay, now we can see with the magnetic field, it gets all tangled up. Okay, so it's a huge mess with eventually these loops and effect from the electromagnetic radiation and all that the magnetic field gets tangled up around the sun. In the photosphere that we see on the visible surface on the sun is what we're most familiar with. Right? And so I'm going to show you some examples of how we can filter out the surface. And then we have a chromosphere. Okay? And so these are the sun's atmosphere. And so these are just above the photosphere and just below the transitional zone, the corona, known as the crown. You might recall we saw the beautiful corona when the moon moved in front of the sun in 2017 on August 21st when we had the total solar eclipse. And that's the best time to view what's called the corona. And corona is outside of the sun. It's the plasma field that extends out millions of miles. Right? And so it put on quite a show during total solar. I want to talk about the sun being a variable star, meaning that it expands and contracts. Expand and contract every about 11 years. Right? So this is kind of a nice profile of where we see the sun is at a minimum when it's at its lowest contraction. Then it expands out. Right? And it expands out, you see there's a lot of activities in between. So it went from being quiet to being expanding out to being very active, then back to a minimum. So the question is, where are we right now? Okay, so here is the nice little profile of the sun's activity. Here we see starting in 2010 roughly, it starts to expand. This is the sunspot cycle and the number of sunspots. So you could see that there's a huge increase in the number of sunspots on the surface of the sun. And then it starts to go down. So this is what we call a solar cycle. We see that over a period of time, the sun expand and contract. And these are called cycle numbers. 19, 20, 21, 22, 23, 24. So we are now just going from 24 to 25. And here we are in 2020, so we're at what's called a solar minimum. And we don't see a lot of sunspots, a lot of activities, not totally blank, but we see fewer. So starting in 2022, we start going upward again. And then around 2025, 2026, will reach peak and then go back down again, right, so through the 11-year cycle. So that's all because the sun is a variable star. And as I mentioned earlier, about the age of about 4.6 billion years old, our yellow dwarf star, the sun, is what's considered to be a middle-aged star, or more or less. Okay? And so the sun, will eventually become a red giant star billions of years from now. It will expand out, and then it'll go nova, become a planetary nebula. And that outer shell of the sun will expand away, leaving behind a little white dwarf. Okay? So nothing to worry about. It's not going to happen for a very long time. Let me show you some wonderful website. This one is called Solar Dynamic Observatory. And this is actually one of the best way to look at the sun. Meaning that you don't go out there and look at the real sun. You can do it right here on the website. It's got a lot of good data. And let me show you some of the do. With the Solar Dynamic Observatory, he has different filters, so it can filter out different wavelengths while observing the sun. So if, for example, you see just plain yellow, you won't see a lot of details. But if you filter out in a different wavelength, you get a lot of good information what's going on the surface of the sun. So that's what it's doing daily, is observing the sun with all these different filters. And so you can actually see those data on that website, with SDO, and to see what the current condition is of the sun. So this is the sun today. And you look at it, okay, this is using a special filter. You see right up the back, right about there, is a bright spot. And then we just saw an eruption. There's the prominent loop right on the edge. Right? So some people will say, gee, it's not a whole lot going on. Well, it's been pretty quiet for a while. But now that we see in this video, which you can also get from that website, you can see the activities on the sun over 48 hours. So pretty remarkable what can be seen from the observatory. Okay. Here's a close-up view of a sunspot that just appeared facing towards the Earth. It's known as AT2765. These sunspots get a label, okay, and it gets recorded. And so this is a variety of little sunspots clustered together. But you can see just recently, around June 9th, there's a big eruption. You can clearly see that. We just missed it, meaning that from that eruption, it missed the Earth. So somewhat fortunate that we didn't get that full impact. So here is one view. We really can't see the sunspot. Right? We see it there, but not much to look at. Let's try another filter. Now we see a little bit more. Okay? And that sunspot right there is about the size of the Earth, or even bigger. Okay? And here's another filter. Now we get a little more of the prominences and such. We see all these scattering throughout the surface. There's a nice big one at the top there of a storm. And this is called coronal holes. Coronal holes, okay, these are a little bit darker. And some of the reason you notice they're at the poles. And that's pretty typical. And so science has been watching for these what we call coronal holes on. And so going back to what we were just talking about, the number of sunspots are pretty few and not much. See here, if we go back to this, there's that sunspot. But if you look at this says spaceweather.com, and it keeps track of the number of days that the sun was spotless. So already in 2020, we have 75%, or 122 days so far, of the sun being no sunspots. But look what happened last year, 2019. There were 281 days That's 70% of the year that the sun was without sunspot. But if you go back to 2015, there was zero. There was sunspots every single day back in 2017. But if you go further back, last time we had quite a few days without sunspots was back in 2008. So this showed you the cycle of the sun with the sunspots, looking at that data. And here's the close-up view, right? And you can see that the very interesting features with the sunspot. There's the sunspot right there, right? And we see what's called a filament, an amazing filament. And there's all of the kind of a alignment with being polarized, right? And so what happened is the sun's magnetic field get tangled up right there. And that's what creates the sunspots. So the sunspots are generally dark and small. And so they can be as big as the Earth or even bigger. But the surface of that area generally is cooler than the rest of the surface of the sun. And it's all associated with the magnetic field being tangled up. And we have one positive, one negative, and they tangled up just underneath the surface. That's what creates what we call the sunspot. Okay? And so the sunspot, the characteristic of it, you see the outer area, it's called penumbra. The core is called the umbra. We have some pores. These are what's called the granules. And then we have spots. So what's happening right now, the general sunspot that we just saw right now, there's about 4 of them in that general area, right? And so sunspots are fun to look at, and you can do it on the website. You can actually get images. Right? So here's another example. Here's a large sunspot. It's about the size of the Earth, and that's pretty amazing that you could see something like that. It's about that size. And here was one back in 1990. It was about the size of Jupiter. Right? And it was huge. And so that was one of the biggest ones that occurred for long. Right? Talk about some of these solar events. We have flares, prominence, and coronal mass ejection. Right? Those are kind of storms that we associate with the sun. And so we just saw that in the video. You can go to this website by Space Weather from NOAA. It's a wonderful website to get the latest information what's happening with the sun. So what's happening is that the flare and the solar wind, the solar storm, interact with the Earth's magnetic sphere. Okay? And it gets funneled down, okay? And that's when we have the arc effect, where it creates the auroras, mainly in the south and north pole. Okay? And why it's important to study it, because when we have a very large flare, it can actually impact the electrical system and grid here on Earth. And then there's been evidence of that. And so it's important to understand the condition of the sun to prevent these power grid failure. It also affects communication with the satellites in orbit. It creates what we call a drag on some of these satellites in higher orbit. It affects also a lot of other things with association with the climate and perhaps the weather. So it has a huge impact in different ways. So what they look for is they watch for what we call coronal mass ejection on the sun. We have a huge eruption like this. And if it's right in line with the Earth, it can take 2 or 3 days, and there's the sun particles interacting with the Earth's magnetic sphere. And it gets funneled down, and gets funneled down, and down just about 60 to 100 miles above the Earth's surface. That's what creates the auroras. And the auroras are color because it's charging that area right there, oxygen and nitrogen and carbon, creating that color that we see these conditions. And then we can have another observatory that's using a disk to block out the sun. You can see the storm coming out from the side. look at those explosions. They're huge. There's the stars in the background. And so you can actually see these storms radiating from the sun. Right? And that's one of the, probably Venus that went by. Then I recommend a website called Solar Ham. They have it's kind of a big dashboard. They have all the things that you can look for on the condition of the sun, images, and the auroras. This is my favorite site to go to for looking at the potential northern lights or auroras here in Oregon or anywhere around the world. So what you see here, that big green donut, is the intensity of the storm that is at the north or south pole. Okay? This is a wonderful site, so you can look at this. There's Oregon right there, and it puts out a red line, kind of hard to see it. But if it's really intense, this thing becomes really bright and it turns even red. If it's red, and then that red line might get extended down to Oregon. The best time to see the northern lights is in the spring or fall. Now we're heading into June, so we're starting to lose any opportunity to see any auroras in the northern hemisphere, but down in the southern hemisphere, they definitely can have some opportunities down there as well to see the north. This is called the KP index, and this is on the Solar Ham website, and this is a 3-day prediction. So you could see a lot of green. So if there's really a strong storm, these turn red. For Oregon, being the 45th latitude, anything that if these bars goes red and gets up to the 7 and 8 and 9, okay, then we have a potential to see the northern lights in our latitude. And so pretty rare, but it does happen. So if you were to watch this KP index, okay, pretty low right now, it's very quiet. But if it gets up into the 7, 8, 9, and it's red, then you go out around midnight and look toward the north to see lights. This is another model that it used. You see all different ways that the sun is turning, okay, counterclockwise. Some of these moving dots are actually the probes, okay, they're orbiting around the sun. The Earth is yellow. There we are right there. There's Mars, Mercury, and Venus, okay, so there's Mars. That has to be Venus, and then there's Mercury, okay? And so see that storm right there. There's that blast, okay? Those are the kind of ones that we watch for. So anything that comes around, if it's heading towards the Earth, then we have potential for the northern lights. Okay? And so this is pretty cool site to look at as well. And you can go to spaceweather.com and look at the images, and you could see that there were a few pictures of the northern lights, but way up there in Canada and Alaska. But we're going to see fewer of these in the coming month in the summer. But down in the south, they have some great opportunities to see the north. Okay? So hopefully that's helpful to understand more about our sun. I encourage you to check out the website and enjoy the sunshine.